All right, folks, it's the weekend because that's when they released the AP Physics 2 free response. So I'm here at home and I'm sweltering a bit. The air conditioning didn't turn on for the summer like it should have. So we're going to have to wait until tomorrow for somebody to come out and fix it up. But anyway, uh, I had a chance yesterday while I was running a garage sale to at least look at these on my phone. So this is not completely unrehearsed, but it's not really that difficult. And I didn't think the AP Physics 1 ones were difficult either. I mean, not compared to what they've done in the past. So I don't know if the College Board's internal data taking is revealing that our country is being filled up with morons or something. But I think that the certainly the degree to which students are being asked to do higher level thinking is noticeably decreased on this exam, this year and last year when they rolled it out. Okay, so we got a sample of N moles, monatomic ideal gas, large sealed thermally conducting container, fixed volume. The small sphere mass ms, there it is in the container. The volume of the sphere is way less than the container, so we can just assume that the container is the volume V. Okay, pressure P, state X. The sphere is initially in thermal equilibrium with the gas. Great, that means the same temperature. The gas undergoes a heating process until the gas is in state Y with the pressure 3P, same volume though, and the sphere is again in thermal equilibrium with the gas, so the sphere heats up too. The total energy transferred to the sphere during the heating process is QS. The graph in figure 2 represents the number of atoms per unit speed as a function of atom speed for the gas when it is in state X. On figure 3, sketch a curve that would represent the number of atoms per speed. Okay, so in state Y, it's going to be a higher temperature, and a higher temperature means that more of the atoms are going faster. So it's the same number of atoms because the same number of moles. So that means that this area has to stay the same, but more of the atoms are going faster. So I'm going to do the same graph here, but this time I'm going to use red. Do I have a red? Since this is hotter, let's use red. That's a hot color. I'm going to draw exactly this, but it's going to rise to a lower peak and a further down peak, and then it's going to asymptotically approach whatever. Okay, lower peak. I'm betting you that's the 2 points. Lower down peak and farther to the right peak, and it has to be the same shape as this. I bet you they won't give you any points if it's not the same shape as that. Okay, derive an expression for the change delta T in the temperature of the gas for the heating process that the gas undergoes as the gas changes from X to Y. Okay, so what I'm going to do is I'm going to say pressure initial, volume initial over temperature initial equals pressure final, volume final over temperature final, and it's the same volume. So we're going to cancel that out. And we're going to say, okay, well, pressure final is 3 times pressure initial. It said that, okay? So P over T equals 3P over T final. So that means that T final has to be 3 times as much as T initial. So the delta T is going to be, oh, I take it back. This is not working for me. I'm not doing it in terms of the initial temperature. Sorry about that. Okay, let's try this again. Let's do PV equals nRT, and I'm going to say this. I'm going to say delta PV equals nR delta T, and if P goes to 3P, then delta P is 3P minus P, which is 2P. So 2PV equals nRT. Okay, there are no subscripts on any of these. I need to make sure that any subscripts I have to do. Oh, delta T. So delta T is going to be 2PV over nR. Hooray. All right. Derive an expression for the specific heat. Okay, so what do we know about specific heat? There's only one equation that really has it. Q equals MC delta T. Okay, well, the number of moles and the P and the V and fundamental constants like R appear in this delta T right here. So I think he's going to come over, and it says QS. So we're going to do Q subscript S equals M of the sphere. So let's put the correct subscripts on it. We really need to put the correct subscripts on everything. C S, and then the delta T is 2PV over NR. So then we're just going to bring the NR up. So it's going to be QSNR up. down 2PVMS, and that's going to be the C. Okay, so that's just really basic plug-in. That's all it is, just basic plug-in. Okay, an insulated container is filled with a liquid of mass ml and a specific heat Cl. The original sphere is submerged in the liquid. The sphere has mass ms less than the liquid, and specific heat Cs is less than the liquid. The initial temperature of the sphere is greater than the initial temperature of the liquid. Later, the liquid and sphere reach thermal equilibrium. Oh, gosh, the delta T of the sphere is going to be way bigger than the delta T of the liquid. Like, why do I even have to say that? Okay, so I am going to say this. I'm going to say Q equals MC delta T. Okay, even though it says, but must include conceptual reasoning beyond algebraic solutions. Okay, so in other words, I'm going to say this. The same delta Q going into the liquid. We were told that the sphere was is hotter initially than the liquid. Okay, going into liquid is the same delta Q. Sorry, same Q leaving the sphere. Okay, but if the liquid has a product MlCl that is greater than MSCS, okay, which it does if ML is greater than MS and CL is greater than CS, right? Okay, which it does, then the delta T for the liquid must be much less than the delta T for the sphere. Now, this does not feel like conceptual reasoning to me. So I am going to try and go further than this. So how am I going to go further than this since I really just argued this equation, and I don't think that's what they're going for? I think what I want to say is I want to say something like this. Let me see if I can figure it out. I'm going to say this. I'm going to say the sphere, the sphere's energy to temperature ratio is much less than the liquids, or something like that, maybe. So the same energy leaving the sphere and entering the liquid means more delta T for the sphere. I don't know exactly I'm not entirely sure what they're looking for here. Okay. So, because I'm not entirely sure what they're looking for here, that's going to be my solution. I'm going to hope that it catches all 3 points. Okay, figure 1 represents the energy levels and the corresponding states for a hypothetical atom. On figure 1, draw arrows to represent all possible atomic transitions that could result in the emission of a photon. A 1, a 2, a 3, 3. Let's really try to make that land on the line. Okay, there's the 3 transitions right there. Just any possible 3 down. Anyway, derive an expression for the wavelength of the highest energy photon that can be emitted. Okay, so the highest energy is the greatest energy difference we can see in the diagram, which is negative 2 E naught minus negative 5 E naught equals 3 E naught. Okay, now E is equal to HF and lambda equals C over F, so F equals C over lambda, so E is equal to HC over lambda. I don't think this equation's on the AP Physics formula chart for Physics 2. I think it was back in AP Physics 1, but this is one that's worth committing to memory because you see it so much. So then that means that 3E naught equals HC over lambda, so lambda will be HC over 3E naught. Yay, okay. A device can emit monochromatic electromagnetic radiation, also known as single color light. The wavelength lambda of the radiation can be varied over a continuous range of wavelengths. Okay, that is impressive. I would love to see this device where you just turn a knob and it just changes the frequency of the color of the light that comes out continuously. Okay, on figure 2, sketch the energy E of emitted photons from the device as a function of lambda. Where is figure 2? Okay, there it is. As a function of lambda for lambda naught equals lambda 4 lambda naught. Okay, I'll just tell you, the first time I saw this, I thought I was seeing a bar chart. Can I just tell you? So I was like, what kind of bar chart is this? Asking me to sketch a graph. Okay, and then I realized, okay, so basically it's going to be this. It's going to be E equals HC over lambda. Okay, so photons with wavelength lambda naught have energy 4E naught. And because this is a reciprocal function, it has the form of y equals c over x. Doubling the wavelength is going to be half the energy, and quadrupling the wavelength is going to be 1/4 the energy. So I'm betting that they might even be checking whether your graph goes through those 3 exact points, not just that it's sloping down and concave down, but that it actually goes through all 3 of those points. A student claims that based on the energy states shown in figure 1, the atom can emit a photon of wavelength lambda naught. It said lambda naught is 4E naught, so I'm going to say no. No, you can't emit wavelength lambda naught because that requires energy 4E naught, and given only the states in the diagram, only the energy differences. What are the energy differences? 1E naught, that's from 3 to 2. 2E naught, that's from 2 to 1. And 3E naught, that's from 3 to 2, 3 to 1 are possible. Now, I am going to make this remark, and that is that every atom actually has state number infinity, which is at E equals 0. And then all the states above that are completely continuous, okay? So these are called free states. So I'm going to make this additional remark. I bet you it's not on the scoring rubric, given how easy all these other questions are. I probably not probing for this level of depth. But I'm going to say this. Even if an electron fell from a free state into the atom, then the additional energies, let's see, from 0 to 2, 0 to 3, 0 to 5, 2E naught, that's infinity to 3. 3E naught, that would be state infinity to state 2. So you could do this, and this, and that'd be 2, 3, and 5. And 5E naught, which is goes to 1, are available, not 4E naught. And I'll tell you this. I mean, I think it's physically possible, although I'm sure it's absolutely rare, for an atom, for an electron, to jump from a state at exactly 1E naught all the way down to negative 3E naught. That would make it 4. I'm not even going to write that. I'm sure it's possible, but it's just ridiculously rare. And I'm sure the person who wrote the question wasn't even thinking about that. Okay, in experiment 1, scientists want to collect data that can be graphed to determine the magnitude B naught of an external uniform magnetic field. The field is directed into figure 1. Okay, so I guess they can't say into the page anymore because it's on the freaking computer, and they can't say into the screen either. So they just say into figure 1 in the region between identical parallel conducting plates that are connected to a power supply of variable EMF E. The plates are known distance d apart, and d is much smaller than the plates so that we're not dealing with edge effects, is what that's for. Okay, in each trial, a device emits a small charged particle with speed v through the region between the plates. E is varied until the spheres move undeflected toward the motion detector. They're basically giving us the procedure right now. They're going to ask us for the procedure, and yet they're okay, whatever. The scientists can vary V between trials. Gravitational effects are negligible. Does it output the value of V? All right. Well, whatever. In addition to the equipment shown in Figure 1, the scientists also have access to a voltmeter, and they don't have access to anything else. Do they know? Okay, there's a known distance d apart. I was looking for the meter stick there. Okay, so they know the distance. Okay, so indicate quantities that could be measured using available equipment that would allow the scientists to determine. B, using a linear graph. That's kind of a sad question. I'm just going to say this. Touch the voltmeter leads to the plus and minus on the power supply to measure the EMF, right? Okay. Also, I'm going to pretend it doesn't say the device outputs the velocity, so I'm going to say use the device to measure the velocities of the particles when they go in a straight. You should have said that. You should have had a little output device here that said, blah meters per second or something like that in a straight line into the detector. Okay. Okay, so that's the answer to A. So now I'm going to vary the EMF on the power supply for each trial, getting data of various EMFs and velocities. Okay, so that's the answer to A2. Describe the method to reduce experimental uncertainty. Okay, now indicate what quantities scientists could graph on the horizontal and vertical axis to create a linear graph. Okay, so I am going to say this. I'm going to say that, and you don't actually have to write this part, when the particles travel undetected, the electric force equals the magnetic force, the QE equals the QVB, so the Q's cancel. Also, delta volts equals E delta distance. So that's EMF equals E times this separation distance D, the separation distance between the plates. So that means that E is EMF over D. So this is going to be EMF over D equals VB. Oh, okay, so I'm going to plot EMF on the vertical, V on the horizontal. So if we do that, we get EMF over V equals BD. Rise, run, slope, rise, run, slope, rise on the vertical, run on the horizontal, slope is on the other side. Has to be all the constants. The slope, so that's the answer to A2, and then the slope is B times D divide slope by D to get B naught or something like that. This is a really awkward question. I don't know. It makes me feel dirty. I'll even draw this B, or shoot, I didn't mean that. E versus V slope equals B naught D. I think if the reader saw this, they would just give me all the points and probably not even read the words, and they would be just absolutely thrilled to save themselves some time. Okay. In experiment 2, scientists want to use a graph to determine the mass m of identical charged particles that all have this charge. In each trial, we're given a speed. Okay, we have B versus R. Did they tell us? Oh my gosh, they didn't tell us the equation. That's new. That's rare that they don't tell you the equation. They usually say the scientists correctly derive. Okay, so here it is. It's QVB. It's force equals MA, folks. Okay, so the force is QVB. The M is M, and it's a circular motion, so V squared over R. So this is a rarity that they did not give you the equation. Most of the time, they actually say, here's the equation that relates the B and the D. So I'm going to bring this over. BR equals mv squared over qv. Well, that's going to nuke. Br equals mv over q. Now, I want to identify rise and run and slope, but my two variables, which are b and r, are multiplying, not dividing. You can't do rise times run. That's not slope. So what am I going to do? I'm going to choose one of them, and it's going to be b, and b is going to get shoved into the denominator and reciprocated, because a number, if you, like, for example, if you take 10 times 0.2, which is the same as 10 times 1/5, that's the same as 10 divided by 5 over 1. In other words, we're just doing keep, change, flip. We're going to keep the r, we're going to change multiplication to division, and we're going to flip the b, okay? And then this is mv over q. So then notice that they gave us the q and the v, and so the m is what I'm looking for. So this will be the rise, and this will be the run, okay? So I'm going to just take my calculator right now. Oops. Let's delete this stuff that came from the P1 test. 0.04, 0.06, 0.14, 0.16, 0.2, and 1.8, 1.2, 0.5, 0.4. Our clue that we needed to reciprocate somebody comes from the fact that as B increases, R decreases. In fact, the other clue is that if you multiply L1 and L2, you get almost kind of the same number all the way down. Not exactly, unfortunately. It means the data won't be aligned when I take L1 and I reciprocate it by raising it to the -1 power. So I guess they don't give you the extra table anymore, which is shit. Okay, so this is going to be 1 over B and 1 over Tesla units, 25, 16.67, 7.14, 6.25, and 5. Okay, so now the label the vertical and horizontal axes with numerical scales. So the quantity is going to be R in meters, okay, R in meters, that's a rise. And then this is going to be 1 over B in units of 1 over Teslas, because that's the run. Okay, they gave me 1, 2, 3, 4, 5, 6. They gave me 6 divisions. So R, I'm going to go up to, let's do 0.51, 1.52. And then the 1 over B will be 5, 10, 15, 20, 25. Okay, so it's going to be 25 and 1.8. Yay. 16.67 and 1.2. All right, 0.01, 0.5. Oh, sorry. Yeah, 0.5 and 7.14. 0.5 and 7.14, 6.25 and 0.4. Okay, so 6.25 is about right there, and then 5 and 0.3. Okay, do I have a straight edge here? Do I have a straight edge here? Do I have a straight edge here? Where do I put my straight edge? Where do I put my straight edge? I have a straight edge here. Where's my straight edge? Oh, there we go. Okay, gotta have a straight edge. All right, so you can either take the slope by choosing 2 points on the line, and I would put open circles on them if it were me. Put open circles because that indicates that those aren't the data points. And it tells the reader that you're doing what you're supposed to do, which is to take 2 points from the line, and the farther away the better from each other, rather than taking 2 data points. The readers are trained specifically to look for that, to look for taking 2 data points and taking the rise over run from 2 data points. Okay, so 0.075, but I'm going to also do a linreg. L1, L2, Y1. Okay, so about the same thing. So the slope I got from my TI calculator is 0.0746. The slope is equal to, what did I say it was? MV over QB. MV over QB. Just MV over Q, sorry. So M is Q times the slope over V. M is the Q. What was the Q? 6 0.4 times 10 to the negative 19. The slope, which I got, was 0.0746 over the V they gave us, 3 times 10 to the 6. That's nice and non-relativistic. Thank you for that. 6.4 10 to the negative 19 times 0.0746 over 3e6. And the mass is going to be 1.59. So I get a mass of 1.59 times 10 to the negative 26 kilograms. Gosh. 6, 7, 10 to the negative 27. Okay. Good job, folks. 9.5 nucleons. Shitheads. Should have made it an even number of nucleons. Good freaking God. These people who write these questions don't even think. Okay. Anyway, now that I'm in an angry mood, I mean, seriously, you can't have 9.5 protons and neutrons. Fuck me. Okay, unless that's some bizarre otherworldly particle I've never heard of before. Okay, I don't even want to do this anymore. A small sphere not shown with positive charge, positive Q, has initial speed Vs in the X direction. And kinetic, I can't get over it. Kinetic, I can't concentrate. Ks when it's at point S. The sphere moves to point T, which will have less kinetic energy. Is it positive? Yeah, because going uphill. It's going to have less kinetic energy automatically because going uphill. The force from the electric field is the only force, so we don't have to deal with gravity. The sphere has a final speed Vt. Are you seriously asking me this? You're seriously asking me which speed, the speed at T is less than the speed at S. I can't believe I'm having to deal with this. Okay, this is insulting. Okay, like I can't get over this either. I'm pissed off. Okay, all right, justify your answer. May include, okay, so here's the deal. When a positive charge moves from low potential to high potential, the potential energy of the charge field system increases. If only the electric force, which is a conservative force, acts on the charge, its total energy stays. Listen, I can't even bear. I haven't even read part B yet, and I'm about to get really pissed. Its total energy stays the same. So if potential energy increases from S to T, then kinetic energy decreases. This makes me cringe. Okay, I feel so. I'm gonna take a shower after this. Can I just tell you? Decreases and speed decreases from. This is worth 3 points, so I've got to get all of them at some point here. S to T. Derive an expression for the final. Oh my God. This is insulting. Okay, I'm having my intelligence insulted. Okay. No wonder I'm changing careers. Almost let that drop. Okay, so I'm going to say this. I'm going to say the total energy, which is this. The total energy at S equals the total energy at T. Okay, so at S, it's negative 3 QV naught because potential energy is QV, plus Ks, and then at T, it's going to be positive 2 QV naught, same reason, okay, plus KT. So then I'm solving for KT. God, this makes me so sick. You bring it over and you get Ks minus 5 QV naught. Please don't tell me that part C is, how did you answer to part B? Confirm or your answer to part C. Here we go. Oh, here we go. A new small sphere. Maybe this might be challenging. Of the same mass as the original sphere, but with a negative charge, is the same initial speed, same mass, same initial speed as the original sphere in the positive X direction. When the sphere is at point S, the force from the electric field is again the only force. The new sphere has a kinetic energy E nu when it passes point T. The new kinetic energy will be higher than the old previous kinetic energy point T. Referencing okay, if the charge is positive, KT equals KS minus 5QV. Is it V naught? Is this supposed to be V naught? Oh, I probably better put V. I did put V naught. Okay, is it lowercase q? Oh, it's capital Q. Let's make absolutely sure I give them exactly what they want, because I'll be fucked if I'm going to lose points on this question that a child could do. Okay, QV naught. But if the charge is the same, doesn't really matter, it has the same mass, but negative, then this makes a double negative, and K nu equals KS plus 5QV naught. So K nu must be greater than KT, since K nu is greater than KS because of the adding. Like, I don't want to just sit here and say like one short sentence, even though this question is easy, because I want to get every single point of this easy ass question. Okay, the adding while KT is less than KS because of, this is not even of the subtracting. Like, this is just, I feel violated. Okay. All right. That's AP Physics 2. Screw it and screw you too.